In this video, we'll look to design a circuit to replicate a distance measuring sensor. So what we'll try and do is replicate the sharp sensor. The sharp sensor worked by sending out light. The light was reflected back, and there's an inverse square law relationship, so the intensity of the light reflects the distance that the object is away. For our design specification, as an example for this, what we're going to do is design a distance measuring system. We're going to use an LED to produce some light. That light will get sent out, reflected off an object, and then a photodiode will be used to measure that intensity, and then that'll give us our distance reading. As discussed in the last lecture, we've got digital alternatives to making some of this circuit. However, I'm going to specify that you're only going to have input lines of a DC voltage supply and a single output. So what I'm doing in this problem specification is essentially saying we need to build this sensor from our analog circuits. So we're not going to use a microcontroller to make life easier for ourselves. Okay. Okay, so in principle, you shine the LED and use a photodiode to measure that intensity. There's a slight problem with that simplistic view, in so much as the photodiode will measure the LED light, but it'll also measure any other light that's present. So for example, it'll measure daylight, it could measure street lights, lights in a room, etc. So it'll be measuring all light. So the trick around this, what you do is you switch the LED on and off very fast, so say typically of kilohertz. And then when you measure this on the photodiode will again measure all sources of light. However, you then look at that signal and only pick out the frequency that the LED is being strobed at. So you can then differentiate between the light that is being produced by the LED and all other sources of light. So in order to do that, we'd use a bandpass filter. So as I said, we've got limited input and output lines, so we can't use a microcontroller to do things like do a timing pulse and measure amplitudes. So we have to do all this with analog circuits. We've got an LED to produce the light and a photodiode to measure it. We need to switch this light on and off at a fairly fast frequency. So we've got a timer circuit to do that. So we discussed our 555 timer in the previous video, so we can use that. So that light goes out, comes back, gets detected by the photodiode. Photodiodes, it depends which type you get, they typically output a current. So what we'll need to do is change that or convert that current signal into a voltage signal. So our signal from a photodiode, we're going to have to use a current to voltage converter circuit. At that point, the voltage might be quite small, so we're probably expecting about microamps out of the photodiode. So even after conversion, we might need to amplify that signal more. So potentially we might need some amplification circuit to improve that signal. Now that signal is going to be composed of the LED light and also all the other sources of light, daylight, etc. So what we need to do is identify the frequency that the LED was transmitting at and filter that frequency out. So we're going to need a bandpass filter to filter that frequency. So we should now have a nice clean AC signal representing our LED light intensity. In order to measure the amplitude, as we said, the amplitude is the measure of the distance to the object. So we need to know the amplitude of that signal. To measure the amplitude, as we discussed in the previous video, we can rectify it and then pass it through a low pass filter to effectively get a measure of the amplitude. Once we've done that, what we might need to do is amplify again. So again, it depends on the previous circuitry, but if that signal is too small, we might need a final stage of amplification in order to achieve this. So a schematic of our circuit is going to look like that. We're going to have an LED being driven by a timer, and that is going to send out light. That light is going to get reflected by the object, and that is going to be read into our photodiode. So we've got a small current signal coming up from our photodiode. So we change that into voltage with this circuit. We might need to amplify at this point. Once amplified, we'll extract our signal of interest, so our LED strobed signal, using a bandpass filter. And then to measure the amplitude of that signal, we'll then rectify and low pass filter it. And then potentially as a final stage, we might want to amplify that signal again so we have a nice strong signal to then read from our sensor. We now have an idea of what circuit we need in order to accomplish making our distance sensor. So now we'll have just a quick comparison with how that compares to the actual sharp sensor. So if we grab the datasheet for the sharp sensor, what we will find is this circuit diagram of how the sharp sensor works. And as you can see, there's a lot of similarities between how that sharp sensor works and how ours works. What we've got is an oscillation circuit. So we're producing this oscillating signal which is driving our LED to produce the light. And then that light gets reflected, measured on some detector, which then goes through some signal processing, which in our case is a bandpass filter, before it gets through to some final circuitry to be amplified and output. So a lot of similarities. We've got a voltage regulator in there, which we'll discuss in tomorrow's series of videos. So we'll cover regulation then, but essentially we've got the same circuit there as the sharp circuit. There is, however, one notable difference, and it is this point in the circuit. And if you see this, the oscillation circuit is being fed to drive the LED, but it is also going into the detection side of the circuit. So the frequency it's being driven at is also being used to analyze the signal. So we did this by using a bandpass filter. So that works. The slight problem with that is that you've got to design the filter specific for the driving frequency. Okay, so it does work, but you've got to sort of design it appropriately. The way they've done it here is it doesn't matter what driving frequency you're using, because it is using that same driving frequency to then analyze the signal. And this is a technique called synchronous demodulation. Okay, so I've put a question mark, so I believe that's what they're doing in this circuit. But it's a very useful technique for sensors such as this, where you know what frequency you're driving at and you want to detect at that same frequency, and therefore you can use that frequency to then extract the signal you want. So I won't go into details of synchronous demodulation, but there's a couple of references here that's worth a read that explains how it works. So that's a useful introduction. And then this article here shows you a circuit on how to achieve it. So I do not want you doing it for this module in terms of doing this for your mini assignment, which we'll discuss shortly. It's important that you learn about filters and how to make them. So I prefer you to go down the filter route for this problem. However, synchronous demodulation is a very useful technique, so it is worth reading up on. So a few final thoughts. We've slightly simplified the problem because we've got a voltage supply going in there to power our circuit, our op amps. the op amps are taking plus or minus typically 12 volts as a voltage supply. If we connect our sensor to our Arduino, for example, that's only got a 5 volt supply. So we're putting in 5 volts, but then we're suddenly using plus or minus 12 volts. So we have simplified the problem a bit. So we don't have to solve that. It's just something to consider. But it's just something to bear in mind that in practice you do need to consider sort of your power supplies as well. The options, a couple of options I've suggested, is what we can do is take our 5 volt power supply from our Arduino and then use a rectifier to change that into plus or minus 12 volts, which we can then use to power our op amps. So we'll discuss rectification in tomorrow's tutorial material. And we actually use this technique when we do this practically in the lab. We actually use a rectifier to change 5 volts into plus or minus 12 volts. The other option we have is to use op amps that use a 5 volt supply and they use ground and 5 volt as their power supply. So again, that's an option. The slight scenario around that one is you've got to then work around a working bias of half that voltage, 2.5 volts. So you kind of get a negative supply. So if you have an AC signal, you cannot have the supply go to minus if the op amps are only supplied with 0 to 5 volts. So you have to work via a 2.5 volt bias, which makes the circuit design a little bit more complicated. Okay, so there are options there, but it's not something we need to worry about for this exercise. It's just something to bear in mind. So to summarize today, it's important to know filtering. Filtering is a very useful technique. It gets rid of all the noise or a lot of the noise in the signal, so you have a nice clean signal. And if you have got a good clean signal, that then makes it easier to perform high amplification of it. And then ultimately, when you feed that into an Arduino or something like that, it then leads to better resolution when you digitize that signal. We have discussed a lot of circuits in the last couple of days. So we started off fairly simple and then they've been a bit more complicated today. But I hope, as you can see, you can actually develop very complex circuits just by using these simple building blocks as a starting point and then putting them together to make these complicated circuits.